Hello, and welcome to today's ACM Learning webinar. The webcast is part of ACM's commitment to lifelong learning. This webinar is brought to you by the Special Interest Group for Artificial Intelligence and specifically the CGI industrial community. We're planning to have webinars on different topics of interest for those in industry and academics as well. And this is Catherine Guo, the membership chair for CGI and member of the CGI Industry Liaison Committee. And I'm a senior researcher at Lockheed Martin Advanced Technology Laboratories. And my research interests are primarily in AI and applications. And Rose Paradis was the previous secretary and treasurer for CGI, a member of the CGI Industrial Liaison Committee. She's a principal research engineer for Leidos, where she works as a data scientist for big data analytics. Her work focuses on data and text analytics, computational linguistics, and natural language processing. And today's presentation is Autonomous Manipulator Solutions for Mobile Robotics by Tom Boyer and Dr. Blaine Levedahl. You can find more info on our backgrounds in the bio widget on your screen. And let me just take a few minutes to go over some of the ACM and CGI information. So I think everybody can read this, and I'm not going to be spending too much time on it. But we do offer educational and professional development resources that bolster skills and enhance career opportunities so that while members can stay competitive in constantly changing world of computing with a range of ACM Learning Center resources that you can find at learning.acm.org. So now you can see those highlights on your screen. And it listed our goals and a few other things that we actually sponsor, especially for people that who just started their careers. So AI is increasingly interdisciplinary area. So your membership actually supports these goals. And if you can join us today by going to the link on your screen for Googling CAI, and both members and non-members are welcome to join our mailing list to receive company announcements of interest to researchers and practitioners. So before we actually start, there are a few more housekeeping items that we would like you to know. So first, the slides will advance automatically throughout the event, but on the bottom panel, you will find a number of really useful widgets and resources. So if you're experiencing problems with the slides or the audio, just press the F5 key in Windows, and which is the command press R if you're using a Mac. Or you can refresh your browser on a mobile device. The worst, you can just close and relaunch the presentation. To control the volume, adjust the master volume on your computer. And if you have questions during this webinar, please type them into the QA box at any time during the webinar and click the submit button. Rose and I will organize the questions as our speakers speak, and he will reserve time at the end of the presentation to address them. This session is being recorded and will be archived, so you will receive an automatic email notification when it's become available. And you can also check learning.acm.org for updates on this and other upcoming webinars. So we have a short survey at the end, and we would appreciate you to take the survey and go into the resources. So today's presentation is Autonomous Manipulator Solutions for Mobile Robotics. It's being presented by Tom Boyer and Dr. Blaine Levedahl. So Dr. Levedahl is Director of Product Development at Robotics. He has 14 years of experience developing modeling strategies and control systems for a myriad of different projects, from collaborative control of autonomous unmanned aerial vehicles to rapid maneuvering control for underwater vehicles to path planning and control of single and multiple robotic systems. Dr. Levedahl joined Alice from Boeing while working on architectures for current and future UAV systems. Prior to that, Dr. Levedahl worked at Feathers Unlimited, Honda Aircraft Company, Northrop Grumman, and as a professor at Nagoya University in Japan. Dr. Levedahl has a PhD, an MS, and BS degrees in aerospace engineering from North Carolina State University. And Tom Boyer is Chief Commercial Officer at Alice Robotics. He leads Alice Robotics business development and operating strategy using his more than 20 years experience delivering innovative connectivity and Internet of Things products to industrial and defense markets. Boyer's focus at Alice is to help Alice customers improve operational efficiency and increase safety performance by implementing supervised autonomous solutions available through Alice Robotics, advanced robotic control, vision, and deep learning products. Prior to Alice, Boyer led product and service launch for satellite terminal products and services targeting maritime vessels that command embedded tracking and Internet of Things solutions for asset management at SAIC and Ravenway, and integrated sensor systems to monitor industrial assets from space, air, and land. And now, without further delay, let's go to the presentation.
Thank you very much for the introduction. Yeah, thank you, Catherine. Appreciate it, and thank you for everyone for attending today. What we're going to talk about is Alice Robotics and their approach to autonomous manipulation software. So, just from an agenda standpoint, I'll give a little bit of background on the company. We'll talk about our sort of market approach and what markets we're targeting. Dr. Levedahl, who's on the phone, will kind of give a deeper dive into the technology. And then we can look through the subsea products that we have in the market today. And I believe there's a Q&A session at the end. So from a high level, Alice is really a robotics software company. We don't build hardware. We try to be hardware agnostic where it is entirely possible. But we've kind of grown out of developing precision robot software solutions for the ROV market, for the offshore oil and gas industry. We have done some work with the Navy and ONR in terms of EOD remediation, but our primary focus for the past couple of years has been in the oil and gas industry, and now we're expanding into space and also land markets for manipulation requirements. We have a pretty strong portfolio spun out of the University of Washington, where we have several patents that we've licensed and then several that we've submitted for. And we've got a pretty broad array of customers from where we operate. We've got a number of subsea customers, folks like Fugro, Oceaneering, Forum that operate ROVs in a lot of different environments. On top of that, we have space industry customers, including NASA, AFRL, some commercial companies such as Maxar and NanoRacks. We are in Fremont. It's an area of Seattle, a lot of great restaurants and a good chocolate facility and plenty of coffee. So if you happen to be in the area, please reach out. We're happy to show you our technology and give you a tour. Just to give some background, where we came from, we saw a discrepancy in capabilities for robotics that actually need to do work. So if you look out in the markets right now, there's been an incredible amount of investment in terms of autonomous navigation and and kind of machine learning to process data to provide decision-making framework or predictive analysis or predictive maintenance kind of configurations. But from a robot that actually is going to go and do work, we've seen there's quite a bit of inefficiency in how you can manipulate objects using a robot, and it requires substantial human involvement. So what that gets to is a one-to-one correlation of you're buying all of this hardware from a robot standpoint, yet to deploy it, you have to still pay that cost for a human to control it. It has some benefit. In the ROV market, it's a necessity because you can't put divers down at 6,000 meters. But from a scalability perspective, it limits the market size for robotics. We do see a lot of constraints in terms of enabling that capability from a latency and processing standpoint. So there are communication links that have significant latency, especially when you look at space, or you have to survive dropouts going into areas that are congested. And with the edge processing coming online now, there's a lot of things that we can do to take advantage of that. But most folks are trying to achieve a full autonomy solution right out the gate, and we think that there's an intermediate step there that can allow robots to scale, take advantage of what's going on from a 5G network perspective, still handle the latency, and build upon the processing capabilities that are coming to market. And that will take the extremely limited use cases for manipulation today and extend that into broader market appeal. So that's how we see the world. And how we plan on implementing it is taking kind of the best of sensor and data inputs with cloud architecture and providing the AI components. So what we're doing is, instead of having a teleoperated solution where a human controls a robot independently, we can use that AI to do human-in-the-loop training. It's a very rapid approach. It doesn't require coding to achieve that training. It just requires one-touch learning process that we're implementing in our control loop, and then that pulls the human out of the loop for actual execution of a task. So what you're, in a sense, doing is automating that task execution in dynamic environments. So you can sit there and say, you need to do this work in an environment, and the robot can go out and do that. And when that work changes, you can rapidly retrain the robot to go do it in the next task. And that will facilitate a much higher ability to do different tasks quicker, driving efficiency, and then bring down your costs because you're less that one-to-one ratio of human to robot to manipulation task. You can train several robots to do a task, they can go off and do it, and you sort of manage that process is where we get into that supervised autonomy construct. From a market standpoint, again, we've got pretty strong credentials in the subsea offshore energy market. We are moving into space where we're working with folks to look at habitat robotics to do experimentations or to do maintenance. The cost of astronauts is becoming significantly high with what NASA is publishing as kind of their next steps. And then when you look at in-space servicing or on-orbit servicing requirements, there is a lot of capabilities that, if they are brought to bear, will significantly reduce costs of extending the life of certain satellite assets in space, which opens up a whole bunch of market. And then long-term, we look at planetary exploration as sort of a big leap in technology that's going to require stuff like our software to enable that manipulation in more autonomous situations. So that's where we're going in space. From a land perspective, we've got a number of partnerships that are starting to come to fruition where we're looking at removing folks from the dangerous and dirty and challenging jobs in these chemical production facilities or hazmat facilities where it makes more sense to have robotics. So we're seeing a lot of traction along these areas. And again, we're presenting here today. Hopefully, if you have interest in working together or see that there's a problem that we could solve together, we're very flexible in how we can do that. We're a fairly small company, so we can make a lot of things happen quickly. Feel free to reach out, and we'll figure out how we can solve real-world problems. With that said, I will be handing off to Blaine, who will walk through more detail of our technology and how we're taking it forward.
Okay, thanks, Tom. So basically what I wanted to start with was the idea that there's been a large amount of autonomy and movement and autonomy for mobility-based tasks. However, robotic manipulation is different than mobility because in mobility you generally are avoiding objects. With remote robotic manipulation, you actually want to come as close to objects as possible and not only contact them. So we generally call this controlled collisions. So the biggest driver for a lot of this, and this is an example here of the current state of the space remote robotic manipulation, where there's operations on basically two sides of the spectrum of autonomy, and that's basically been driven by safety considerations. On the one side, which is the right side, you have full task autonomy for limited sets of tasks. Basically, this is only works in a very structured environment where the environment is known extremely well. You can do a lot of a priori testing on the ground to formulate the autonomy and test the autonomy and verify an operation prior to deployment. Then what you do is you basically run this level of autonomy. Examples include docking with probe and capture, remote rover mobility. On the other side, when your full automated tasks don't work or you don't have enough knowledge about the environment, or the environment changes, or something out of the ordinary happens that you didn't predict, you have to revert back to incremental scripting. This is a very limited task autonomy. Basically what you do is you do small incremental trajectories. You test them on ground surrogates, on simulations. You upload those, run them, then you look at the small motion, you analyze that after it's been downlinked, and then you move to the next small incremental motion, and the process repeats. It's very long operational times because of the ground testing and the delays. There's similar, even though this is an example of space, similar type operations occur in offshore as well as land-based hazmat. There's not really a viable option for the in-between. Our solution to the in-between is what we call operator-centric supervised autonomy. Supervised autonomy has been around for a long time, but it's generally implemented as almost a top-down approach, where you start with this high level of autonomy and then try to introduce things as fallback scenarios. We implement it in more of a bottoms-up approach, where we support the operator, where support of the operator is really the top priority. This is not really that much different than the natural evolution of what we commonly call the autopilot now with aircraft. We didn't set out to provide a fully autonomous flight control system from the get-go. Instead, what people developed was functions that supported the pilot, such as a yaw damper, attitude hold, altitude climb, functions that would support the pilot that were then combined into different ways to support autonomy. On the right side here, you have the Society of Automotive Engineer definitions for autonomous cars. Notice that they cover what we consider the spectrum of autonomy, and then we have different product offerings, which Tom will discuss more later, and how they span the different levels of the spectrum of autonomy. So why is this approach beneficial? Basically, there's two reasons. First, as depicted in this figure, you can see that the degree of autonomy, there's two dotted lines. One is the operational cost, and a notional depiction of the operational cost for having an operator provide the autonomy. You notice that it starts out at high cost and decreases. The other dotted line is a notional example of the development cost. Notice that full autonomy development cost is very high. but for operator control or a low degree of autonomy, it's very, the cost is basically nothing for development. So there's an optimal sweet spot in there, and it's generally not at local direct control, and it's not at full autonomy. It's in between, and so this basically supervised autonomy and being able to scale up and down on the spectrum of autonomy as we approach it from a bottoms up methodology allows us to operate at the optimal level of autonomy or degree of autonomy. The second part that's beneficial is that you can field operational systems earlier and then scale in the field. The ability to provide this operator in the loop, as well as operator on the loop allows you to perform the 4 typical steps of verification. Identifying new operational use cases and establishing requirements, identifying test criteria to verify against those requirements, defining acceptance criteria, and then finally performing the tests with operator on the loop such that it's a safe condition. There are 2 key capabilities that we have integrated to provide this benefit. The first one is workspace perception, and the second one is manipulation primitives. By workspace perception, I mean generation of a 3-dimensional dynamic digital twin, and as well as real-time machine learning object identification, labeling, and tracking. Manipulation primitives are basically similar to your autopilot functions that I was mentioning, like your yaw damper, your altitude hold, your pitch hold. They allow for direct control, direct end effector control, and these auto manipulation functions such as virtual fixtures, slippery limits, tactile feedback, trajectory playback, etc. In summary, these 2 key capabilities allow a remote operator or high-level algorithm that could provide cognition instead of the operator to visualize the workspace, understand the workspace, and manipulate objects within the workspace. For those that are interested in a bit more detail, here is a general flow diagram of the perception and a couple of auto manipulation functions that are supported by the perception. The perception flow is basically to create the 3D model of the workspace, ID and classify objects in the workspace, assign attributes of objects in the workspace, track objects and attributes in the workspace. And having all of that information about the workspace then allows one to perform auto manipulation functions to supports essentially those auto manipulation functions that the operator can use individually as an operator in the loop type scenario, can combine them together and perform task assignment as an operator on the loop, or in more extreme cases, as Tom was mentioning, or more structured cases, they can perform full autonomy by wrapping even more autonomy around those auto manipulation functions. The ones listed here, operation near limits, they basically behave in what we call slippery limits, where you get visual and tactile feedback near joint limits and collision boundaries. Once again, these objects are tracked, their dynamic motion is tracked in the workspace, so you can use those as collision boundaries, moving collision boundaries. In motion compensation, where we're removing the relative motion between an object and the workspace and the base of the workspace using the manipulator, virtual fixtures, and playback of posed trajectories. Motion compensation assistance is one of the primary auto manipulation functions that we found to be most beneficial, especially in a subsea environment. Basically, what we're doing is we are reducing the workload by removing the relative motion between the object in the workspace and the base of the manipulator. So if there's a ROV and the arm is attached to the ROV, and you've got an object that's floating where the ROV is moving, you can remove that motion using motion compensation assistance, and the operator only can perform the operation as though the two objects are stationary relative to each other. So in this next video, you will see the operation of that. I'll let you read the subtitles that describe the events as they unfold. Should mention that this is an example of our early tank testing and motion compensation. Tom will present a more recent one later. In this, you're generating a three-dimensional, generating an image from a moving camera. In this situation, instead of the ROV moving, the ROV is considered stationary, but the object is moving this back plane. You're able to freeze time. And then once you're able to freeze time, you can generate a virtual fixture. Once you generate that virtual fixture, then you are able to advance forward and backward along that virtual fixture. One can think of virtual fixtures as basically a way to constrain the motion. It's not so much like a trajectory where you're refined, where you're forced to travel along that trajectory. The system is able to adapt to dynamic motion in the workspace such that it's not just purely a trajectory, it's almost like a guide. You can notice the virtual fixture. The pilot only has to operate using a forward, backward, and closed gripper, open gripper buttons. You can see the arm is automatically compensating for the motion of the backplane, and the operator doesn't have to deal with that, significantly reducing the workload. Once he performs the gripping motion, he's able to pull off the sling. Another example that I would like to run through of our assistive features is how do we allow the user to interact with their three-dimensional digital twin to speed up operation of precision manipulation tasks in unknown or unstructured environments. This supports variability of targets and operation with latency, bandwidth, and dropouts, specifically in the space. You'll notice that the three-dimensional model that's generated within the workspace is limited in the fidelity of the point cloud. Oh, like this one is not available. Well, the video is available online, and I believe will be sent out later. So. With that, I will pass it back to Tom, who will continue to present some of the products that we have integrated these technologies onto. Thank you.
Thanks, Blaine. So as I discussed earlier, we have subsea products that are in the market now. This OLIS Master Controller is the first instantiation of the software. Because of the way the industry is set up, we built some custom hardware. What you see in the slide is a pendant arm. That's a legacy controller for what I would say is the large percentage of manipulators that are in that market. So we incorporated that to help transition folks that were used to using the pendant to a more user-friendly software configuration like we have, where we hope to eventually remove that requirement that does a couple things. It helps further that automation process where you can kind of point click and have the arm go do things without really a lot of human intervention. It also dramatically reduces the cost of the unit. This pendant arm is probably 60 to 70% of the overall cost of the unit. Getting rid of that will help drive it down, and for further market adoption, we think that's necessary because folks aren't going to want to pay quite that much. From our product standpoint, the things that we've brought to market are basically this replaces existing controllers that are out there that haven't been updated in 20 to 30 years. We have the control pad and touch screen, which across all markets isn't as interesting, but for the subsea, it was definitely a big change. Some advantages just across the board is the software in this instantiation is fairly easy to integrate different arms. So we've put in a universal robotics arm with this controller. We've done many different cobot and subsea arms with it, and are progressing further down that path with space arms. Another interesting thing that this allows, and this is set up for the subsea market where they have a requirement to be able to teleoperate the robot remotely so that they don't have to send folks out on the ship. In the typical scenario, they are tethered to the ROV and have a fiber link to it with the controller connected. But that cost and some other factors are driving the industry to have folks stay onshore and be able to operate it remotely. So what we've created is a fairly easy way to drop in control locally and then also remotely. It would require 2 controllers, but basically you can VPN in using a controller onshore to a controller offshore and control the ROV. Because you're looking at typically using things like satellite links, there's a half second to a second delay, maybe even a little bit more depending on the latency of the network. That does create challenges, but we believe some of the work we're doing in our next product that we're working with partners to field test right now will help mitigate that risk. Really what this is where our value inflection comes into play. With that controller, we can provide that direct one-to-one setup like we had discussed earlier. In this case, we're now providing a way to model the real world and the objects you wish to manipulate. And then we can track targets, select targets and track targets, provide motion compensation for dynamic environments. So in the subsea world where you have the ROV that can be moving, or in space where you have 2 objects moving, we can deal with that dynamics and essentially filter it out from the operator perspective so that they don't have to try and grab something that's moving with the arm, because that can be very complicated. We allow the computer to handle a lot of that. And then we can also put in safety and keep out zones so that we can further drive cost reduction in terms of damage or insurance and those kinds of things, because with a lot of the arms that are operated today, there aren't those constraints, and they tend to break as a result. This video that I'll show is an example of some testing we did in the tank with our partner at Forum. As Blaine was discussing, the motion compensation and 3D modeling can be shown here. So this image at the top left is our controller software interface, and you can see the 3D model there in the center screen. I'm not sure why it just reset. Hopefully everyone can see it. I can send out links if need be, but the model gets generated. The arm is tracking on the T-bar, so it's basically the ROV moving up and down, and the arm maintaining a point location relative to that without the manipulator moving or the gripper actually moving. And then what it transitions to is you see the ROV dropping, and there's the automatic deployment, capture, and pull out of the T-bar in the tank. So and it's playing through here. So you'll see the arm reach out and grab while the ROV slowly dropping. That's where we can automate that whole process of seeing an object and reducing the pilot burden to go out and grasp it and pull it while moving. So that will help deal with the latency, because in effect you are able to path plan and execute that task against that object. The next layer on top of it, as we talked about, was the task training and task assignment. And this is really where you build in the autonomy perspective. So you're able to recognize objects and assign tasks to those objects. This was an initial survey testing we did on anodes in the subsea environment for oil and gas pipelines. Using deep learning techniques, we were able to achieve almost a 97% correct identification of the anodes through the videos. I want to say we did a training segment on roughly 20 to 30, and then when we looked at the full-scale images, it was a couple hundred, and we were able to train the system very quickly using the one-touch human-in-loop training, and then execute. So this is kind of a first out the gate. We're obviously working to get to closer to 100%. I'm not sure what level is achievable, but with the supervised autonomy situation and dealing with semi-structured to unstructured environments, we believe there's areas in there where you can automate the system and allow it to operate and then pull back when it hits a condition that it doesn't recognize, so the human can step in and retrain it around that particular situation. But this will build into folks that are building overall mission planning scenarios with autonomous systems. We now are able to enable that manipulation task so that you don't have to just do inspection and observation. You can actually use the robot to go in and repair and fix things. And we think that's what's driving, or once we cross that hurdle, that'll significantly drive growth in the robotics market and opportunities for everyone. Just the last couple slides here. We've got a lot of news coverage over the past year. Feel free to search some of these, and you'll find some articles about the great work we're doing in space and subsea and even land. And then this is our contact information, so if anyone wants to reach out, they have Blaine and I's email. Feel free to contact us if you have questions or partnership opportunities. We'd love to discuss those further. And with that being said, I will hand off to Catherine, I believe, to wrap things up. Thank you, everyone.
This is Rose Paradis. We're going to be doing some questions and answers now. So what we'd like to do is, if anybody hasn't put in any questions, if you click on the Q&A button, you can actually ask a question and we'll try to answer it. So some of the questions that came in, one of them was, do you think that something like the Edge TPU for more robotic autonomy is a useful device running neural networks? For Tom and Blaine.
I think we're going to have to defer this one. Oh, go ahead, Tom.
Yeah, go ahead, Blaine.
Oh, I think we're going to have to defer this one. We've got, so on staff here, we have, unfortunately he's not on the call, but one of the guys that handles a lot of the, our machine learning we haven't really looked down that direction, and unfortunately I don't really have an answer, but hopefully we can address that question maybe as a follow-up. We'll be taking some of these questions and we'll post answers to them. So if we could, maybe table that one for to answer post presentation.
Yeah, and I think generally speaking, there's a lot of, so right now we use GPUs for a lot of the processing requirements for the AI and the machine vision and whatnot. But there's a lot of investment going into the network architecture and even the chip architecture that drives to lower cost, lower power type systems. And I think the thing from our perspective is, I don't know a lot about the Edge TPU specifically, but as industry goes that path, because we're a software company, it's easy for us to scale with that progression. So hopefully that kind of answers your question without being too specific. but I think we're poised to benefit from that. But and we're in a lot of ways our capabilities are driving that requirement across the industry. But I don't have a specific answer of whether the edge TPU is better or not.
Okay. Another question that came in is, does supervised autonomy include cooperation between operator and robot, or only control?
So we're focusing on supporting the human operation of the robot. So it is cooperative in that there's a shared operation to perform the task. So for example, with like the motion compensation, the robot handles the tracking, and the operator only has to work with, basically deal with the grasping part of it, the advancement along a fixed trajectory and the grasping part of it. So essentially reducing the robot is cooperating with the human to reduce the degrees of freedom and the workload of the human. If the question is focused on collaboration, where the human and the robot work in a shared environment, such as like on an assembly line, we don't really focus on that aspect of things. That's we don't do the collaborative human-robot collaborative control in that sense, where they're two independent entities that are working together to accomplish a task. We focus where they share a task. That's kind of confusing, but I hope that makes sense.
Okay, thank you. Another question is, when do you know a product is ready for launch production? Does it depend on your client's specifications, or does OLIS have a set failure rate that applies to all projects?
So when we look at a product, we're trying to, as a company and trying to, become profitable like we all are, it's really important to get the product market fit correct. So that means working with a broad array of customers within that market, finding out what they need from a robotic standpoint, and then consolidating that to a product that meets the majority of those needs. So we go through very rigorous testing to deploy a product. Once it's out in the field, obviously we have a support infrastructure to support it. From a metric standpoint, it really is around what the market tolerates and what the regulatory and infrastructure is going to support. So in a lot of ways, that regulatory infrastructure hasn't been defined yet, and that's something that we continue to work with industry to figure out. But we by no means want to deploy products that fail and cause additional issues, which is why I think it's important that the human on the loop or supervised autonomy construct is well understood, because what it does is it sets up situations where once the robot encounters an operation that it doesn't understand, it can revert back to a safe state where a human can step in and take over.
Okay, great. Here's another question. While 5G is around the corner, is computing power at the right economic sweet spot at the robot?
Of course. So if you want to buy a lot of stuff, we're happy to sell it. No, I think 5G is a big enabler for real-time systems, especially at a global scale. I think the latency will help quite a bit. If you look at how 5G is architected, it's really tailored around the connected car market. And so there'll definitely be benefits to that. I think from from where we're fitting our products in the industrial market, we might see some benefit, but our experience is we've seen infrastructure that's very dated just because of the depreciation cycles in industrial manufacturing and operations. We're still working with standard definition cameras in some regards. So I think overall 5G is a good thing. I just think the pragmatic reality is some of these field robotics are going to have to deal with legacy systems for quite a while.
Okay, the next question is, from your experience, do you think having more data for AI training will improve object manipulation tasks?
So obviously, yes. If you have more data for AI training, that will improve your understanding of the scenario, of the situation. However, you don't want to wait to have 5,000 images of something. There's other ways that you can generate those images through synthetic simulation-based approaches that people are doing, and as well as databases that exist of images, so you don't have to have the actual data. But at the same time, the more data you have, the more training you have to perform. So we use a combination of real-time training algorithms that we've developed, as well as deep learning approaches. And the balance between those kind of gives you this optimal efficiency in training. Like, you want to hit a certain metric. How do you hit that metric very quickly? So if you have more data, great. If you don't, then you want to try to use whatever data you have available efficiently, and that's kind of where we focus.
Okay, this question was, I think, somewhat answered, but let me just repeat it for those. This person who wrote the question is a student at a university in the UK and enrolled in Robotics and Meaning of Life module and talking about health and safety regulations they're exploring, has a thought experiment, the Isaac Asimov iRobot 3 Laws of Robotics. And the question is, what is your opinion to keep the human in the loop?
That's a very broad, I guess, question. I'll try to answer it. So, I mean, I think I'm of the standpoint that full autonomy for fully scoped all scenarios is I mean, it's almost like you asymptotically approach the ability to have full autonomy. I think having an operator in the loop allows you to do a couple of things. One, it gives you a fallback plan. Two, it gives you checks and balances. I think it's good to use robots for the things that they're good at doing, and I think it's good for humans to do the things that they're good at doing. Human beings, in my opinion, are very optimal for a large parameter space. We don't necessarily have to do the same thing with robots. Robots should be good at focusing on specific tasks and answering questions that require a level of inference and fidelity that we human beings don't have the patience to tackle, but we should still use that information. So to me, it makes a lot of sense to have an operator, involved in the task at all times. Now, that's what's nice about supervised autonomy, is that you can scale how much the operator is involved in the task. If it's a menial task like picking up something and putting it in another place, then just let the operator tell it what to do, or let the thing kind of decide that it needs to put it there. If it's a more complex task like deciding whether to buy or sell stocks, it's good to have all the data, but it's not necessarily good to have the algorithm making the decisions for you. Now, I know people will disagree with that, and this is a highly debated topic, but I personally think it makes sense to keep the human in the loop, not only from an ethical standpoint, but also from a practical standpoint, because there's always going to be things that you don't run into. I guess I would say that Murphy is also at play.
Okay, thank you. couple more questions we have time for. How are mistakes or errors noted and corrected?
So I saw this question. What specific errors and mistakes are you referencing? Just if the robot makes an error or mistake?
Yeah, right. If the robot made an error, like how do you correct that?
Yeah, so well, there's a couple layers to that. I think one of them is it an inherent software flaw or bug? Hopefully we identify a lot of that in testing and field demonstration. If it's a flaw in the training mechanism, then I believe that's something we'll need to revisit. I don't know that we have a solid answer on how we would account for training issues, because that's the human side of it. But we would look at a framework where we can validate and verify the operational capabilities to a task and do the in-field verification prior to any execution. So, there'd be several layers of tests. How we would incorporate that feedback, I think, would really depend on the market and kind of the customer base. But we would want to make sure that we're operating at the highest level of availability and reliability for whatever requirement we're up against. So, and that will drive costs. And so you'll see different cost metrics for operating on, very dangerous oil and gas infrastructure versus if you're trying to just unplug and plug in a router at some facility.
Okay, thank you. We have one more question. When the object recognition is done using the human in the loop, like that you referenced on slide 18, how are all the objects and positions of the objects that could be recognized handled? I'm guessing, is it a finite set of objects then that the robot has to deal with?
So the objects in the scene are defined into or partitioned into known objects and unknown objects. For the known objects, obviously the robot will be able to label those and track those. For the ones that are not known, this is where the operator, helps, because the operator can then label those very quickly with our software, and then we can generate basically a large amounts of training data and do machine learning in real time, what we call one-touch learning, to allow the robot to be able to identify that the next time around. So it's an ever-increasing amount of objects, but it's driven by what the human or what the operator perceives as to be important, and this is the important aspect for scaling, right? The alternative would be that if you have to anticipate everything that the robot is going to encounter, as opposed to, well, I'm going to train the robot while he's doing this, and he's still going to give me benefit while he's out there, even though he might not know everything about the situation. I can help him better understand the situation, and that becomes my role as an operator, as opposed to trying to directly command him or just let him go free. I can help him, better understand his environment, and that's kind of where we focus a lot of our effort is that side.
Okay.
I think the last question.
Yeah.
Oh, okay. Go ahead, Catherine.
All right, go ahead. Yeah, because I was thinking that.
There was one more question
okay.
About, is there a common procedure to test those auto manipulation functions, which I think you kind of answered, but I don't know if you want to say more about that.
A common procedure? You mean in terms of like verification or validation? Yeah, so I mean, there are different phases of the auto manipulation functions, and so it's kind of like if you were to test what's a good one? The virtual fixture generation, for example. You know, you would look and make sure that you're generating the virtual fixtures, and the virtual fixtures are able to track with the objects in the scene once the label has been applied. I think that's answering the question. I might not understand exactly the details of the question.
Yeah, I think that's fair. I don't have any further information about that. So, okay, Catherine, go ahead. I think we're set for questions.
Yeah, we're set for time today, and then we're getting close to 1 o'clock. So I'd like to thank Tom and Blaine again for this informative presentation and those insightful answers to the questions. And a special thanks to each of you for taking the time to attend and participate today. This webinar has been recorded and will be available online in a few days at webinar.acm.org. And you can find announcements on upcoming webinars and other ACM activities at learning.acm.org and generally at acm.org. So if you could, just please fill out our quick survey, and that's where you can, if you could, suggest future topics and speakers. We would really appreciate it. And the link is right showing on the screen. So on behalf of the ACM, SIG-AI, Tom Boyer, Blaine Levedahl, Rose Paradis, and myself, thanks again for joining us, and I hope you will join us again next month at our next webinar. Please also take a quick minute to do the survey and take a look at the ACM web pages and join our group. And that would conclude our webinar for today. Thank you.